Hi everyone, it's so good to be with you. And of course today what we're going to do is we're going to investigate probability in a little bit more detail. Here we are going to take the rules of probability that we've gone over already, and we're going to extend our knowledge by applying them to different situations. In a way, we're preparing ourselves for what might come up in a test or exam. But that's not the important thing. The important thing is that you've got a good picture of what the terms mean and how to apply. So let's not waste any more time. Let's make sure that we're on track. And so the first thing what we're going to do is we remember that we've got our concept map, which deals with the key ideas. Now, for learning about probability or anything in maths, remember mathematics is a learning subject. Don't let anybody fool you. There are certain things that you're going to need to learn, and amongst those are things like your definitions. And so when we talk about theoretical probability, you must know how to define theoretical probability. You need to make sure you know what the sample space, what the word complement means, how to deal with two events, and what the difference between mutually exclusive and events that are not mutually exclusive. Where does the word intersection apply and where does the word union apply? What rules are we going to do? So make sure that you've got these key big building blocks in place so that when you do a question, you can relate back to them and you can pick up the key terminology that will help you get the right answer. So let's just do a quick review of what the important factors are. So remember, we've done this lots of times. The sample space represented S. We say that the probability of the sample space is 1. That relative frequency is what we do when we do an experiment. It might not give us the theoretical outcome that we were predicting with probability, but if we do enough of them, if we make this very big, then we will get close. These two will get closer and closer to each other if we do lots and lots of trials. We recognize the word complement means that if that's the symbol for complement, it means it's not part of X. So the number in the complement is the number in the sample space minus those in X, and the probability of calculating the complement is 1 minus the probability of X. Recognize we can show this in terms of the Venn diagram, the blue area representing the complement of X. Remember the idea of union. Union is the bigger thing that we're talking about. It gives us less conditions. The outcomes can either be in one set, X, or in set Y, or Z, or whatever one you want to talk about. But they can be in either one of them. It's not very strict. It's a bigger amount, even though we use the word or. Whereas intersection is a much more defined process, and it's smaller, it's stricter. So, for example, you're going to say that 2 conditions are required. You can be somebody with blue eyes and somebody that is taller than 1 meter. That is a smaller group of people than if we were to consider the whole sample set. So even though we use the word and, remember it's limiting. It's very important that this word and, you recognize it's not opening things up, but it limits, it adds more conditions. Very, very important. When we have mutually exclusive events, these are events that cannot happen at the same time. So you can't be in a situation where you have, for example, a card that you're doing with playing cards, and you say, I'm wanting a card that is a heart and it's black. Well, sorry, that doesn't exist. Okay? You can't have a black heart. Sorry. Even if you are really cross with somebody, don't have a black heart. Have a cheerful heart, and it will go a long way. So mutually exclusive events are things that can't happen together. There's no intersection between them. So we recognize for mutually exclusive events, when we're calculating the union of mutually exclusive events, remember union means or, we can take the probability of one plus the probability of the other. And that's our or rule for mutually exclusive events. But if we are going to deal, and we've illustrated them like that, if we're going to deal with things that are not mutually exclusive, that means there's something in the intersection. Then we're going to say the or here is going to have an added part, and it's this subtract the intersection. Now, why do we have to subtract the intersection? Well, because there's a contribution to the intersection from set X and from set Y, and yet we consider the intersection as only being one thing. So we've got to take away the intersection when we're adding those two other bits together. So in this part, we're only going to count the intersection once. We count once for the intersection, but here you're counting twice. There's part of the element in the intersection there and there. That's why you've got to take away the intersection units. So there we go. We recognize in things that are not mutually exclusive, there are going to be elements here. And so they belong to X, they belong in X, but recognize they also belong in Z. And so we can double count them. In the intersection, we don't double count them, and so that's why we apply the OR rule. Right, I think it's time to take all of those rules, which are really cool rules, and apply them to some problems. Let's have a look at this particular one, which is one of my favorite dilemmas. And I'm sure you might struggle with it every now and again as well. Which decision should I make? Should I purchase a particular vehicle or a particular item or another item? Well, Bongani's in that situation. He's going car shopping. He's decided on the model. We're not going to say what model it is. Let's just say it's a really nice car. We don't want to give the owners of the car or the brand of the car any free advertising, but it's a really nice car. But Bongani can't make up his mind whether he wants the red one or the blue one. They both look really nice, but he's got to make a decision. So he's trying to decide, and he's narrowed down his choice to a red car or a blue car. He can only buy one car though. Most of us, it takes a long time to buy a car. Better to save, and then you can buy it for cash. Not many of us have that discipline. But Bongani can buy one car. Recognize it. It's either a red car or a blue car. Now they tell us some details here. There's a probability, a 58% probability that he'll buy the red car, and there's a different probability of buying the blue car. So how these statisticians came up with these probabilities, I don't know, but maybe they measured some things and they came up with these numbers. Let's just leave that those are the numbers that we've got to work with. And we've got to answer some questions about Bongani and his purchases. So, what's the first question? And the first question is, what is the probability of Bongani choosing the red car? Of not choosing the red car? Oh, I thought we were given a gift there, because we were already told what it was for choosing the red car. We were told what the percentage is, but what's the probability of not choosing the red car? Well, do you remember what rule we're going to adopt here? Well, it must be the complement rule. Remember what the complement is. All of those things that are not in the set that we're looking at. So we're going to ask ourselves, what is the complement of the red car? So if we say P not red, then what we've got to recognize is, first of all, the probability of red we've been given was 58%. We've been given that. That's up there. But what is not red? Well, that's going to be 1 minus the probability of the sample. Sorry, not the probability of the sample, the probability of the red. The 1 stands for the probability of the sample. So we're going to recognize of not choosing the red car. There are certain things that he can do. He can probability of the sample minus the probability of the red, which is 58%. And if we do that, we recognize this is the probability of red dash, okay, not red. We're going to say 1 minus 58. Now, if we want to do this correctly, we're going to say 58 is actually 0.58. And when we do the subtraction, I think you can see that this is going to be 0.42. Okay, 0.42, which turns out to be 42%. Now, that is the probability of not red. Not getting red is higher than the blue. We'll have to think about that. What might those probabilities include? But I hope you can see how we've applied the complement rule. Let's move on to the next question. So what is the probability of Bongani choosing either the red car or the blue car? Well, let's have a look. Now, recognize that the red car and the blue car are not overlapping. So these are mutually exclusive. You can't have a car that is red half of it and blue the other half. So we can apply our rule of the OR function here, the probability of either choosing red or blue is going to be the probability of red plus the probability of blue. And if you do that, it's not difficult to see that we're going to add these two together. 58% plus 38%, and I think that you can see that comes to 96%. So there's a 96% of him choosing either the red or the blue. Well, what do you think that difference of 4% can be? Well, let's have a look at our next question. And here is the next question. It says, what is the probability of not choosing either the red car or the blue car? We recognize we've almost got the answer, and we've established already that the probability of choosing red union blue was going to be 96%. So the probability of him not choosing, not red or blue, is going to be 1 minus the probability of red blue. And if you do that, you'll see that that is going to be 1 minus 96, or 0.96, which gives you 0.4, which is 4%. So, guys, what does this mean? Well, it means there's a 4% chance that after all his dilemma, Bongani is going to walk away and not buy either of those cars. Maybe his partner will twist his arm and say, Bongani, I think you can just carry on using your old car for now. Don't buy the red car or the blue car. 4% chance of Bongani not purchasing any car at all. Well, that was an interesting idea, and it hopefully helps you to calculate both theoretical probability and apply the complement rule. And we've also revised a little bit about the OR rule for mutually exclusive events. So I think we've ticked a couple of boxes in applying the rules. Let's take a break. We'll be back to apply some more rules after this.